Today, we are pulling back the curtain on one of the most fundamental and, frankly, clever tricks in all of computer science. We're talking about how a machine that's really only built to add numbers can also be a total master of subtraction. It really sounds like a paradox, doesn't it? If a computer's brain, its processor, is built for just one thing, how in the world does it do the exact opposite? Well, the answer isn't to build more complicated hardware, it's to use a brilliant mathematical shortcut that completely changed the game for computing. Let's dive in and see how this elegant solution actually works. So here's our game plan. First, we'll look at the fundamental problem. Then, we'll explore the ingenious way we code negative numbers. We'll walk through a real example, step by step, then understand the math that makes it all tick. And we'll finish up with a strange little exception that programmers always have to keep an eye out for. Okay, let's get right to the heart of the issue. At the most basic level, computers are all about simplicity and efficiency, and that creates a really specific challenge. Just think about it this way. Building a totally separate piece of hardware just for subtraction would be like having a second engine in your car that's only for driving in reverse. It's clunky, it's inefficient, it's just not a smart design. So the goal for the pioneers of computing was to figure out a way to handle both positive and negative numbers using the absolute simplest hardware they could, and that was an adder. So if you can't build a dedicated subtractor, you've got to get clever. The whole challenge really boils down to this. How do you represent a negative number in binary in such a way that adding it is the exact same thing as subtracting? The solution, it turns out, is a neat concept called complements. Okay, so the very first idea anyone had was something called the ones complement, and it is incredibly straightforward. To get the negative of a number, you just flip every single bit. Every 0 becomes a 1 and every 1 becomes a 0. Super simple, right? Well, this easy approach has one huge deal-breaking flaw. And this is the problem in a nutshell. If you take the ones complement of positive 0, which is just a string of zeros, you get a string of all ones. This creates a negative 0. Now, having two different ways to represent the same value, 0, is just a nightmare for a computer. It forces the hardware to do extra checks and adds all this complexity that engineers were trying to get rid of in the first place. And enter the hero of our story, 2's complement. This is the system used by pretty much every modern computer on the planet. It builds on that first idea, but it adds one tiny, crucial extra step. You still flip all the bits, just like before, but then you add 1 to the final result. It sounds so small, but believe me, that single change fixes everything. Just look at this side-by-side comparison. That little add 1 step completely gets rid of the double 0 problem. Poof, gone. In 2's complement, 0 is just 0. And this makes all the arithmetic incredibly clean and simple. You can just add numbers and the right answer pops out without any weird exceptions or extra hoops to jump through. All right, enough theory. We've talked about how it's supposed to work. Now let's actually see this amazing trick in action. We're going to do a simple subtraction problem, but we're going to do it exactly the way a computer would. So our problem is 69 minus 12. But remember, the computer can't subtract. So it does this clever reframing. It turns the problem into an addition, 69 plus negative 12. So our first job is to get our numbers into binary, and then find that special 2's complement code for negative 12. First things first, here are our numbers in a standard 8-bit binary format. 69 is 01000101, and the number we want to subtract, 12, is 00001100. Now let's turn that positive 12 into a negative 12. Okay, here's exactly how the computer does it. We just follow our two-step rule. First, we take the binary for 12, and we invert every single bit. That gets us the ones complement. Then we just add 1 to that result. And there you have it, 1111104. In the world of 8-bit 2's complement, that is negative 12. And just like that, the hard part's over. All that's left is a simple binary addition, the one thing our processor was actually built for. It's going to add the binary for 69 to our brand new binary for negative 12. But there's one last little rule to keep in mind. If the addition creates a final carry bit that overflows past our 8 bits, the computer just throws it away. It's ignored. And here is that final addition. You can see the binary for 69 up top and our 2's complement version of negative 12 on the bottom. The processor just adds them up, column by column, and this is the result it gets. So what happens when we convert that binary result? 0011 1001 back into a decimal number we can understand? Well, we get 57, which is, of course, the correct answer to 69 minus 12. The trick worked perfectly. So we've seen how it works, but the real question is why? Why does flipping bits and adding 1 magically transform a subtraction problem into an addition problem? Well, the reason is actually rooted in some pretty elegant math. This is a great way to think about it. It's a bit like the odometer in an old car. You know, when it rolls over from 99,999 back to 00000, it's basically doing a kind of wraparound math. Two's complement uses a similar idea. To find the negative of a number, it's like just subtracting it from a huge number that's just beyond what the system can even hold. Okay, here's the secret sauce. The fancy name for this is radix complement. But the reason our invert and add 1 trick works is simple. Think about the biggest possible 8-bit number. It's all ones. Subtracting any number from all ones is mathematically the exact same thing as flipping all its bits. So that's our invert step. The add 1 step then just completes the equation. It's a brilliant shortcut for a much more complex operation. Now, this system is nearly perfect, but it has one very famous, very weird little quirk. It's an edge case that happens because the range of numbers isn't perfectly symmetrical. So with 8 bits, you can represent numbers from positive 127 all the way down to negative 128. You see that? There's one more negative number than there are positive ones. So what do you think happens if we try to find the negative of that most negative number, negative 128? We should get positive 128, right? Well, let's see. So the binary for negative 128 is a 1 followed by all zeros. We apply our rule, we invert all the bits, which gives us 0, 1, 1, 1, 1, 1, 1, 1. That's positive 127. Then we add 1, and we end up right back where we started, 1, 0, 0, 0, 0, 0, 0, 0. That's right. The negative of negative 128 is negative 128. This happens because positive 128 simply can't exist in an 8-bit signed system. And this one weird number is a classic trap for programmers. If you're not careful, an operation like, say, taking the absolute value of negative 128 might actually give you a negative number back, which can cause some really bizarre bugs in your code. In the end, this one beautiful trick, Two's complement, is just a perfect example of smart, efficient engineering. It allowed us to build simple, fast hardware that has powered our digital world for more than half a century. And it really makes you wonder, doesn't it? What other invisible, elegant bits of math are hiding just beneath the surface of the technology we use every single day?